In this video, we want to take a look at solving nth order homogeneous equations with constant coefficients. Now, we've already done second order homogeneous with constant coefficients, and it turns out that the process here is very similar. So let's illustrate this by working through three examples here. So the first example I have here is just third derivative minus the second derivative minus the first derivative plus the function itself is equal to 0. Now, as we did with second order, we're looking at this saying, I need a function that can combine with its derivative and its second derivative and its third derivative, and all those can somehow look enough alike that they combine to be the zero function. That stuff cancels out. So the primary candidate for a function that looks like its derivative is an exponential function. So I've got a guess of y equals e to the rt, and hopefully I can find a value of r that makes this work. And so if y equals e to the rt, the derivative is r e to the rt, the second derivative is r squared e to the rt, and now the third derivative is r cubed e to the rt. Plugging all of those into the equation, I get this thing right here. So there's the third derivative, the second derivative, the first derivative, the function, and it's equal to 0. There's a factor of e to the rt in each of those that can be pulled out. And then you've got a product of two things equaling 0, which means either one or the other is 0. But the exponential is never 0, so it's got to be the polynomial. And just as in second order equations, we end up with a polynomial equation, which we call the characteristic equation. In this case, because it was a third order differential equation, I got a third degree polynomial. And notice that the coefficients here, 1 minus 1 minus 1, 1 are the same as the coefficients here, 1 minus 1 minus 1, 1. Essentially, y turns into a 1, y prime turns into an r, y double prime turns into an r squared, y triple prime turns into an r cubed. So you don't really have to do all these steps every time. I just did them here in the first example because we want to illustrate the process and remember what it is that we're actually doing. So this equation comes from that process, but you don't have to do the process every time. You just can write it down, save yourself time. Now, it's the matter of factoring cubics, or when we do higher order ones, factoring higher order polynomials. The question is, how do you factor? Now, there's a couple of things I do. One is I look for factoring by grouping, which actually this one works. If I factor, this isn't how I did this one. What I notice on this one is that if I plugged in r equals 1, 1 minus 1 minus 1 plus 1, that would be 0. So r equals 1 is a root of that polynomial, which means r minus 1 is a factor. So if I know that r minus 1 is a factor, then I can just do polynomial long division or synthetic division, or there's various methods to find the other factor here. And in this case, the other factor is r squared minus 1. So then the r squared minus 1 I recognize as a difference of two squares, and I can factor that into r minus 1 and an r plus 1. So what I see here is I see r equals minus 1 from this factor right here is a solution, and r equals 1 from both of those is a solution. So we have 2 out of a possible 3 solutions, right? 2 of them turned out to be the same. So this one, r equals minus 1, is telling me that e to the minus t is a solution to that differential equation. Likewise, r equals 1 is e to the t is a solution of that equation. And then what does this other one tell me? Well, what did I have to do when I was in the second order case? Well, if you had a repeated root, then you had the exponential and you had t times the exponential. And that's the same thing that happens here. And so with this root, I get e to the minus t. With the root of r equals 1 there twice, you get an e to the t and a t e to the t. And so the general solution to that differential equation would be as I have it written here. Now, my next example, is, it's curious to me because when I start off doing differential equations, the first ones I look at is y prime equals y. Give me a function whose derivative is equal to itself, right? E to the t. Great. And then you'd find, well, any constant times e to the t. And then you could say, well, how about functions whose second derivative is equal to themselves? And of course, e to the t works. Is there another one? And the answer is yes, there was another one, e to the minus t, right? Because y double prime equals y would be y double prime minus y equals 0, r squared minus 1 equals 0 for the characteristic equation, and so r is plus or minus 1. And you get e to the t and e to the minus t. Now, r to the fourth, we haven't actually solved this one before, but I'm pretty sure we've talked about it, that the fourth derivative equaling, so y to the, fourth derivative of y equals y. I think sine, well, e to the t and e to the minus t certainly work, but sine and cosine would also work as well, right? Take the derivative of sine, you get cosine, take the derivative of that, you get minus sine, and then minus cosine, and then back to sine again. So 4 derivatives get you back to where you started from. So for fourth derivatives, we've got 4 nice functions. How about third derivatives? Do you have a function whose third derivative is equal to itself? Well, certainly e to the t. But any others? Are there 2 other functions that work? And so we can find them this way. When is the third derivative equal to the function? So when is the third derivative minus the function equal to 0? The characteristic polynomial here, not the characteristic polynomial, the characteristic equation is r cubed minus 1 equals 0. I recognize this as a difference of 2 cubes, which would be r minus 1 times r squared plus r plus 1. This is unfactorable, and so r minus 1 equaling 0 would tell me that r equals 1, and this other thing equaling 0 would give me, I use the quadratic formula here, negative 1 plus or minus the square root of 1 squared minus 4 times 1 times 1, all over 2 times 1. Anyway, I get minus a half plus or minus the square root of 3 over 2 times I. Okay, so the r equals 1 tells me that e to the t is a solution, which I already knew. But these other ones tell me the other solutions, and because they're complex numbers, I'm going to end up with an exponential part times a sum of sines and cosines, right? So the real part here becomes the coefficient up there, e to the minus a half t, and then times the quantity c2 cos radical 3 over 2t plus c3 sine radical 3 over 2t. So I have to admit that I'm a little disappointed that the 2 other solutions are not simple functions. I mean, they're decaying harmonic motion, right? They're e to the minus a half t cosine radical 3 over 2t and e to the minus half t sine radical 3 over 2t. It's like, this seemed kind of weird. That being said, though, they're kind of weird, but think about it on the complex plane, right? That the 3 solutions here, 1 plus or minus a half and radical 3 over 2, are the 3 cubed roots of 1. So they're equally spaced around the origin. The origin's here. You got 1, 2, 3 solutions. So in some ways, the functions are equally spaced. I don't know. Anyway, decaying harmonic motion, sine and cosine here, with particular frequency and particular, decay rate here, are the 2 other functions whose third derivative is equal to the function you started with. Let's do one more example. This one a little more complicated. So I've got the 5th derivative minus 3 times the 4th derivative plus 3 times the 3rd derivative minus 3 times 2nd derivative plus 2 times the 1st derivative equals 0. Okay, well, the characteristic equation would be r to the 5th minus 3r to the 4th plus 3r cubed minus 3r squared plus 2r equals 0. And then I've got to solve for r. Okay. Well, the first thing I noticed is that there was no plain old y in here. It wasn't a plus y. So there's a factor of r in everything here. And so that's the first thing I would factor out, leaving a 4th degree polynomial in there. then, well, the thing I do is I try factors of this number divided by factors of the coefficient in front of the biggest thing. In this case, since the coefficient out here is a 1, then I'm just going to try factors of 2. So 1, 2, minus 1, minus 2. But sure enough, if I plug in r equals 1 in here, 1 minus 3 plus 3 minus 3 plus 2, minus 3 plus 3 cancel out, and then the 1 plus 2 is 3, and the minus 3 is there, so r equals 1 is a solution. So I can factor the r minus 1 out, do polynomial long division or synthetic division, or just figure out what the other factor is. Honestly, I just figure out the other factor. If this is an r here, this has got to be an r cubed. And if this is a minus 1 here, then that's going to be a minus 2 right there, because it's got to multiply to be positive 2. So I start with this end and that end, and then I can figure out what needs to be here. Because for instance, I already know I've got a minus 1 r cubed, but I got to end up with a minus 3 r cubed. So if I put a minus 2 r squared there, this gets multiplied by that r, then I got minus 1 minus 2, which would be a total of minus 3 r cubes. I can then look at the r squareds in a similar way, but that was the r squareds. I can look at the r's and figure out what has to be there anyway. So I've got this now factored into a 2 linear factors and a cubic. I ought to be able to factor that cubic further. R equals 1 doesn't work again. 1 minus 2 plus 1 minus 2. Nope, doesn't work. Negative 1 I don't think works either. Minus 1, minus 2, no, that's like all negative. So R equals 2 is my next choice. 8 minus 8 plus 2 minus 2. Woo, that one works. So R minus 2 is a factor. Again, divided in polynomial long division, synthetic division, however you want to get this last factor, r squared plus 1. That I recognize as a sum of 2 squares, which is not factorable with real coefficients. So I can stop right here and say I have, this one tells me r equals 0. This factor equaling 0 tells me r equals 1. This one gives me r equals 2. And this last one gives me r equals plus or minus I. Okay. Now, one of the things that I don't think we ever ran into in the second order ones is we didn't do a problem that didn't have a y in it. We always had y double prime, y prime, and y. We didn't leave the y out. So we haven't seen this happen before, that r equals 0 is one of the roots of this polynomial equation, which means, remember, our assumption was, although we didn't write it down here, our assumption was we were looking for solutions of the form y equals e to the rt. Well, in this case, with r equals 0, e to the 0t is just e to 0, which is 1, right? So what we're saying here is that a constant is a solution to the differential equation. But actually, you know, that makes sense, because if the function is a constant, the derivative is 0, and the second derivative is 0, the third derivative is 0, the fourth derivative is 0, the fifth derivative is 0. But since there's no y in here, you don't actually see that constant. You just see all its derivatives, which are zeros, and it adds up to 0. So yes, y equals a constant is definitely a solution to this one. And that showed up with this r equals 0 being one of the roots of the characteristic equation. Okay. R equals 1 gives me an e to the t, r equals 2 gives me an e to the 2t, and the r equals plus or minus I with a real part of 0 here. I don't have the exponential decay. I just have the sine and the cosine, and the coefficient in front of the I there is 1. So cos t and sine t, and the general solution looks like that, right? The process is very much the same. Because the characteristic polynomials will always factor into linear and quadratic factors, I know that I'm always going to be getting solutions for r that are either real or come in complex conjugate pairs. The real ones give me exponentials, or if you have a repeated root, they give you a t times an exponential. And then the complex conjugate pairs give you an exponential times sine or cosine. Okay. There is one other thing that could pop up here that I should mention, and that is if you have, like in this one back here, where did we have it? We had a repeated root on this one. But if you had a cubic that was a perfect cube and you just got you got the same root 3 times, well, you'd use, right, for instance, if this one was 1, 1, and 1, I would have used an e to the t, a t e to the t, and then I'd use a t squared e to the t. That is, each time you have that extra root, just multiply your answer by another t. And you can double check that that actually works, but that is what works. Okay. So anyway, the process is remarkably similar to second order. You just have more of it. Yay.